knows now? Yes, thanks. Okay, so imagine you are building a distributed system and you are interested in building a router component that is able to distribute load from a client to a set of services. And so, as you might imagine, in such a system, what would a typical message flow be? Well, there must be a message from the client to the router at first, and the client will send this message as some kind of combination of a tag and the payload, the tag being the type of the message being sent and the payload being the data of the message. And in this case, the client will send a reference to itself so that other components in the application can reply back to that actor reference. And then the router is supposed to send or forward this request to one of the services, maybe depending on the load of the services. And then finally, the service is supposed to reply back to the client. And in this case, we would like that the service replies directly back to the client so that messages don't overload the router if they are the reply messages. So even though this system looks kind of simple, it's still quite difficult to implement because every part of the application has to do exactly the right thing. And if we look only at the expectations of the router itself, the router expects that it gets some request message from the client, and then it says that it will forward it to a service, which then will directly reply back to the client with a reply message. And if we analyze these set of expectations more carefully, we can see that it actually is about 3 types of expectations. So the first type of expectation is about the expected actor interface. The router should be able to understand request messages sent from the client. Then we have an expectation about the payload of the message. As we have seen, the client sends a reference to itself to the router, and that should be part of the payload of the message. And then finally, we can have expectations about the expected communication behavior of the actors receiving the messages. So we can say things like, if the router receives the request message, it should forward it to the service. And then the question is, can we make the lives of developers easier by making all of these actually hidden expectations explicit through code? And indeed, we have done this for quite some time. It's called design by contract. And in sequential programming language, there has been a lot of research covering this area. And the idea is that we have functions, and those functions are exposed under some type of contract. As you can see here, the factorial function has a single contract attached to it, saying that the argument should be strictly greater or equal or greater than 0, and then the return value will also be equal or greater than 0. And the idea of design by contract is then that you can use this math module, and if you use it in an incorrect way, like in the user module over there, where we call it with a negative number, we expect to get some kind of error in our application, and the application does not continue with the wrong value. And the idea is that this error information also includes a piece of crucial additional information called blame information, which points to the module that was responsible for the contract violation. And in this case, it's clear that the user module is to blame, so that's where the blame will point to. And so the central question of our paper then becomes whether we can do something similar for distributed actor programs. And then secondly, whether or how the blame assignment information or semantics will be affected by this. And there is already some work that deals with this question, but there are a few limitations in these papers. So first, they cannot really express communication chains. So what we have with the service, that it should reply directly back to the client, that's something that cannot be expressed, and it is usually because they consider only 2 components between which the contract holds, and those are typically things like clients and servers. And because we have only these 2 components, usually the contract systems do not allow to express things about the receiver of individual messages. So what we propose is a new contract system that aims to be able to express all of these expectations that I have talked about before, and also overcomes these limitations. And so for the actor interface, we propose actor interface contracts. For the payload, we propose message contracts. And then for the expected communication behavior, we propose communication and receiver contracts. And I will only talk about the three last contracts, but you can find more details about the interface contracts in the paper. So the goal of our contract system would be that we would be able to express something like the communication pattern that we have seen in the introduction of the presentation. And you can see here, this is a final contract, and you can see the three messages that need to be sent: the request, the forwarding of the request, and then the reply. And you can also see how the three expectations are mapped into contracts. And I will now give a bit more detail about the individual components of this contract. To start with the message contract, and the message contract is actually kind of a special type of contract because it combines many different constraints. So it combines what the expected tag of the message is supposed to be. It also constrains what the payload of the message is supposed to be, and then also what the receiver of the message is to be, and what the communication behavior of the receiver of that message is going to be, or must be. And if we return to our example from before, when we wanted to express that the payload of the message should contain an actor reference, indeed, we can easily express this in this message contract by saying that the tag should be a request and that the payload should contain an actor reference, which we denote by this actor predicate. Then, receiver contracts, they can encode what the expected receiver of the message is supposed to be. And so what we had in our example was that the router should forward the request message to the service. And we encode this by using a predicate. Here it's called specific recipient, which says, okay, if you send this message, you should do it to the service actor. But this is just one example of a predicate, but you can imagine many different predicates, and in fact our contract system allows for any predicates to work as long as it returns true for a matching expected receiver or false otherwise. Then finally, the final type of communication contract that we will talk about is the communication contract. And here you can see on the right-hand side of the slide that I present one type of communication contract, the ensures contract, which states that the messages embedded within this ensures contract must be sent by the receiver of the message contract on the left. And actually, maybe you have noticed, but this introduces some kind of recursive structure in our contract, because messages can now have communication contracts, and communication contracts have message contracts, and that's how we can express these communication chains that I talked about. That's how we can express contracts on the service, for example, when we start our communication chain in the router. So, to show you how this looks in our contract system, let's take a look at our expectation that the service should send its reply directly back to the client. This looks like this, and you can actually see that I have included a part of the contract that is also talking about the forwarded message, but I have highlighted here in a red border the reply contract. And you can see here that we encode this expectation using an ensures communication contract, and that the message contract then says that the text should be reply. Maybe there are some reply contracts, and so on and so on. And what's interesting here is that we can have dependencies on the payload of messages that were earlier in this communication chain. For example, here we say that the receiver of this reply message should be equal to the first value of my original payload. And if you recall from the introduction, the first message in its payload, it contains this actor reference to the client actor. So now we have indeed specified that the service should reply directly back to the client. So to summarize what we have done so far, we have created a contract system to express communication chains that can depend on earlier communication behavior, as well as introduced contracts on the expected receiver. So now I would like to talk about how blame assignment works in this system. And to do that, I will return to sequential contract systems, regular contract systems, in which you just have two parties. I've used the client and the router from our example here as well, but it can be any type of party. And each party in such a contract system gets a blame label. In this case, we have the router which gets J and the client which gets K. And in the middle of these two components, we have a contract monitoring boundary, which states in this case that the message, and you will see in a moment what dashed means, should be dashed. And so if we look at what would happen if we send a message with a solid border, so it does not satisfy the contract because the border is not dashed, we will now see what happens in that case. So the message gets sent, and so importantly, attached to this message will be the blame labels that correspond to the router and the client. And the idea is that then once some contract violation occurs, the first element of this set of blame labels will be blamed for the contract violation. And so when the message is about to cross the contract monitoring boundary, what we have to do to make our blame assignment correct is, of course, to swap these blame labels so that the client label is first and the router label is second, in which case, because our message does not have a dashed border, we get a blame error, we get a contract violation blaming the K, the client. Now, if you would like to apply this type of blame assignment in a distributed setting, you will see that there are some kind of problems that you run into. For example, in a sequential program, we just have call returns, but in a distributed system, we don't really have that. We only have messages that we send to somewhere, and then we might get a reply back. Even worse, the router might not even send the reply back to the client, and we have seen this in our introduction example. The router sends the request to the service, and then it doesn't send any reply back to the client. So this is also kind of problematic from a blame assignment point of view. So what we propose instead is to keep these two parties that are involved with the contract. So we keep the client and we keep the router. We keep their blame labels. And so what happens is that if we just consider communication between the client and the router, we don't have any problems with using the same contract semantics as before. But the interesting thing happens once the router forwards the request message to the service. And now you will notice that we only have one blame label left. And this is because once the router has accepted a message from the client does not have any obligations left to fulfill. And so we only need to keep this one blame label corresponding to the router, corresponding to the server party of the contract. And then the final question becomes, what do we do with messages that do not originate from the router, but in some other component down in the communication chain? Well, we just keep this blame label attached, because in the end, the router has started this communication chain, so it is to blame for anything that goes wrong within this communication chain. To validate our work, we first evaluated it on expressiveness, and to do so, we implemented a number of reactive design patterns. You can find those in the artifact. And we also provide a formal proof of blame, correctness. And to finalize, I will just give a high-level overview of how this works. So this blame correctness proof that we propose in the paper is based on some work by Dimolas and others. And there they introduce the notion of ownership. And they say that a party in the contract system can only be blamed if the value that caused this contract violation is owned by that party. And to do this, you have to annotate the source program with some initial ownership annotations, which then get propagated throughout program execution. And then once the time comes, if there is a contract violation, we just need to make sure that all the blame labels align with these ownership labels. And if so, we have a correct blame assignment semantics. And the main challenge, but you can find more details in the paper, was to relate communication behavior to value ownership, but I don't have time to go too deep into this. So to conclude, we've proposed a contract system to express constraints over some kind of expectations. We have expectations on the actor interface, on the payload, and on the communication behavior. We have introduced or proposed a Bram assignment semantics for this contract system, and we have proven this correct. You can find more details in the paper, and the artifact is also available at the following link. Thank you.
Any questions? So I have a question. An actor might just not do anything and get stuck on something in a distributed system. Does the contract system notice?
Whether the actor got stuck?
Well, for example, the actor that's supposed to forward the request, right? What if it just loops or blocks on something and just doesn't send the message on?
So, yeah. So in our language, we don't support blocking operations. So every call is asynchronous, basically, including message send. So that's something we don't have. But if you have like an infinite loop, we don't account for that yet. But what I can say is that all of the contracts are checked after a turn of an actor. So that kind of already limits the part where it can get stuck between message handlers or something.
Okay, okay, thank you. Okay, so I've learned to wait a few seconds if somebody will step up. Okay, thank you so much.
Okay, thanks.